In the previous example, we tried to calculate the temperatures and also pressure at all states. And using those properties, then we also calculated to investigate the net amount of work and back work ratio and thermal efficiency. So let's talk a little more about the thermal efficiency. Even though we kind of use the all values to calculate the thermal efficiency, we also can derive an equation to express the thermal efficiency to show what is the key design parameter to define the performance of the ideal Brayton cycle. Now, we assume that your working fluid still is an ideal gas, air, and its specific heats are constant. Okay? You already have done homework to derive very similar equations about thermal efficiency for the ideal Otto cycle, and also you are going to do the kind of same derivation for the diesel cycle as well. We can do the very similar steps to derive the thermal efficiency equation for the ideal Brayton cycle as well. Okay, and this derivation is your homework. But with the almost kind of similar steps, now when you try to derive the thermal efficiency equation for the ideal Brayton cycle, now we can derive the equation this way. And clearly what you see is your thermal efficiency equation is a function of the pressure ratio. Okay, so the pressure ratio dictates how efficient your ideal Brayton cycle should be. And when you try to draw a plot of that thermal efficiency as a function of pressure ratio, then we can draw the plot like what we see in the left-hand side. Okay. So it clearly shows us that in order to improve the thermal efficiency of the gas turbine, we should keep increasing the pressure ratio. Okay, so that is pretty clear. But when you see the realistic feature of the gas turbines, most gas turbines are designed to have pressure ratio in between around 5 to 20. Okay. So I'm not going to talk about the lower part of lower limit of pressure ratio, but now we are wondering about why we should have that kind of higher limit of your pressure ratio. Wouldn't it be better to keep increasing the pressure ratio? Because for sure from this plot, the higher pressure ratio would be more beneficial to us. But why should we limit the pressure ratio at around 20? What is a realistic feature that would limit that pressure ratio? In order to understand that limit, we have to understand that if you increase the pressure ratio, we also increase the temperature at the turbine inlet. Then if you really think about the material of the turbine blades, that material should have a certain limit that endures that high temperature gas. So the too high temperature at the inlet of a turbine, in the case T3, can cause the thermal damage of turbine blades, and that is not good for the operation. So that is why we have certain higher limit of pressure ratio. And now, what would be the effect of pressure ratio to the power? So as we discussed in the previous slide, you should have a certain limit in terms of maximum temperature that goes into the turbine. So we always think about the fixed maximum temperature. In the case, for example, 1000 Kelvin, but it could be higher. But the fact is that we always have a certain fix of maximum allowable temperature depending on the material that we use for that manufacturing of the gas turbines. And also we have certain minimum temperature that is usually at room temperature. And now with those two design restriction, let's try to increase the pressure ratio from very low pressure ratio to very high pressure ratio. And when you think about very low the pressure ratio, for example, pressure ratio at 2, then you can easily imagine that the the TS diagram would be very shallow rectangle kind of shape. Okay, and the area inside this closed loop should be your network. And as you see, the network should be very slow, very small. But now let's try to increase the pressure ratio more and more. Then it becomes a more kind of nice area between inside the closed loop. So what it means is that as we increase the pressure ratio, then you probably have more and more network at a certain point that you can make a maximum, like 8.2 for that example. But what would happen if we keep increasing the pressure ratio above 8.2? Then your entire shape of your closed loop now begins to make more like a tall, narrow trapezoidal shape. Okay, as you see, RP equals at 15 for that case. And again, the area now begins to be decreasing again. So if you really think about what would be happening in terms of the area of your closed loop cycle, then it can start from low value and increases to make a certain maximum network. Then it decreases, as we increase the pressure ratio. Then the question is that how can we find that optimal pressure ratio that would make the maximum net amount of work? Okay. So in order to answer that question, let's try to assume again your ideal gas working fluid as the ideal gas with a constant specific heat. Okay. Then your net work can be calculated by turbine work, in the case Cp T3 minus T4, minus compression work Cp T2 minus T1. Okay, so that is your net amount of work. Then in order to make this equation the net amount of work maximum, we have to satisfy the derivative of net amount of work to Rp should be 0. Okay, so from this relation that we can get the Rp that makes your net work maximum. Okay, now I'm not going to show you the whole details of this derivation, and I will leave this derivation to your homework problem maybe. But if you really look at the result of it, then this Rp maximum can be related with your Tmax or T3 over Tmin or T1 powered by K divided by 2 times K minus 1. So by using this equation, then we can approximate the optimal pressure the pressure ratio that would give us the maximum net work from the ideal Brayton cycle. So in today's lecture, we have learned about the ideal Brayton cycle. The ideal Brayton cycle is the base model of gas turbine engines. The ideal Brayton cycle is composed of 4 processes: isentropic compression, constant pressure heat addition, isentropic expansion, and constant pressure heat rejection. Okay. Isentropic compression is occurring in the compressor, and isentropic expansion process is happening in the turbine. And the compressor and turbines, those are connected by one shaft. In order to do the thermodynamic analysis of the ideal Brayton cycle, we have to use the first law of thermodynamics for an open system. When you think about the steady state. So you should be very familiar with how to use the first law of thermodynamics for an open system. So if you are not yet, please go back to the previous lecture notes and learn more about it. Our objective of doing the first law of thermodynamic analysis for the gas turbine or ideal Brayton cycle is to get the net work and back work ratio and the thermal efficiency. Okay. Now, We also see that the pressure ratio is the key parameter for the ideal Brayton cycle. And pressure ratio, tells, governs how much work that we can extract out of the gas turbine, and also how efficient we can design the gas turbine. Thank you so much for your time, and I hope that you have learned the gas turbine and the ideal Brayton cycle from my lecture. And in the next lecture, we are going to talk about the more realistic features of the gas turbine. Thank you so much. Bye-bye.